Too much going on in here. No assignment due today. First time this week. We've avoided a Wednesday deadline, which is good. We do have a project due on Friday, though. So keep that in mind. Again, if you'd like any help with that, I'm happy to get you started and or get you unstuck. Last time we were talking more about Turing machines in general. We found that we could add quite a few things to Turing machines without changing the class of languages that they accept. That was nice. It'll allow us to be able to answer some more complicated questions with regards to Turing machines without making extremely complicated Turing machines. As you may have seen if you started working on the homework, even fairly simple languages can have large Turing machines, lots of states, lots of transitions between those states, and that grows to be pretty gross. So sometimes it's nice to have those extra frills that you can add to Turing machines, and you know that they accept the same language class. So if you can make a Turing machine with one of these extra features, then you could make a Turing machine without it. It just will save you a lot of sanity. The last thing we talked about was non-determinism in Turing machines, and we found that, in fact, non-deterministic Turing machines accept exactly that same class of languages as well. So the book has a much better version of this. I just want to get the intuition across to you that you can simulate a deterministic Turing machine with a non-deterministic Turing machine and vice versa. So they are equivalent. And this becomes useful when we talk about the next thing that we're going to discuss today, which is the concept of a universal Turing machine. And the introduction to this is that there is still one big difference between what a Turing machine, as we have discussed them so far, can do and what a modern computer can do. And that big difference is that the computer is reprogrammable. You can take a program written on a computer and you can edit it. Or you can have the computer run a different program. It's generically, the CPU on a computer is able to take in a generic program, whereas a Turing machine has to be designed as a program. There's one program per machine, instead of a machine that can read an arbitrary program and execute its instructions. So we need some way to be able to simulate that on a Turing machine. So how we're going to do it, I think I alluded to this a couple of days ago. I never know what I talk about anymore in here. But we are going to feed a description of a Turing machine into the Turing machine. So we'll have a Turing machine, rather than dictate its program, we're going to have a Turing machine that reads the instructions, basically the definition of another Turing machine as part of its input. So now what the program is that the Turing machine reads is a tuple. It's going to be a machine definition in binary, followed by an input definition in binary. So there are two pieces to the input. So first piece, Turing machine, second piece, an input to that Turing machine. And now we want to read in that Turing machine, emulate that Turing machine with this Turing machine on the input that is also given to it. Does that make sense as to what that is? It's like a modern computer running a program that you write. You write the program and you tell the computer, run the program that I just wrote. And also here's the input that I want to run on this program that I just wrote. And the computer can do that without being pre-programmed to run exactly your program that you wrote. So that's a universal Turing machine, and we'll come back to how to use this. For the moment, we're just going to assume that it is possible. We could take a Turing machine, break it down into those components. Here are its set of states. Here are its set of transitions. Here is the legal tape alphabet. Here's the legal input alphabet, etc. With that definition written out in binary, we could parse that and determine what it does. Then we could construct a Turing machine from that emulates that. Then we'll run the input from there. So the result from this is that any Turing machine can be encoded in a finite binary string. And if we have an encoding of a Turing machine in that binary, we can decode it uniquely into the exact program that it represents, the exact logical sequence, the exact logic that it accepts or rejects, the exact logic that it produces when it turns an input into an output. That's not just yes or no. So now we have a way to emulate a Turing machine with another Turing machine, which is a very important concept in computer science. One way that we do this, and that I like to suggest people think about it, is, let's say the PlayStation 2 is a phenomenal console. Wouldn't it be great if we could play PlayStation 2 games on a non-PlayStation 2 console? And in fact, there is an emulator that can play everything on the PlayStation 2 except on a PC instead. And what it is doing is it is literally emulating how a PlayStation 2 works. It's mapping the internal representation of a computer to the internal representation of a PlayStation 2, and it is emulating exactly that. So that's what we are doing here, just with another version of itself, a Turing machine emulating another Turing machine. To be able to explain more about this universal Turing machine, we're going to need to take a quick aside and talk about a mathematical concept. And that is countable and uncountable sets. Anyone seen this idea in another math class or off on your own research as you've gone about and, I don't know, played around academically on the internet? So sets can either be countable or uncountable. By this, we mean that there's a place that we can start, and we can then iterate, if it's countable, every element of that set eventually. We don't reach necessarily termination because it can go on to infinity, but you cannot give me an element of that set that the process does not eventually reach. So can someone give me a set that is countable? What is one of those? Let's make it fun and make it an infinite set. Give me an infinite set that is also countable.
Set of all integers.
Set of all integers is interesting. How do we know that that is countable? Let's start with a subset of that, because I think that it'll be a little bit easier to see why. So like the set of positive integers is countable. We start with 1. The successor to 1 is 2. The successor to 2 is 3. There's always a successor to the next number. And to prove that it's countable, I would say it is impossible for you to give me a positive integer that this algorithm, this process that starts at 1, defines the successor as the current number plus 1 and loops that forever, wouldn't reach. You can't give me a number that that process wouldn't get to. You tell me 10 million, it'll get there. You tell me 10 trillion, it'll eventually get there. You tell me 10 vigintillion, it will eventually get there. You tell me 10 Googleplex, it will eventually get there, long after the universe has ended. But it would get there if given enough time. So set of positive integers is countable. We can define, kind of like an inductive proof, a starting point and a succession function that allows us to generate the next element of the sequence, and then we can prove that there is no element of this set that is not eventually reached in that process. How about the set of positive even integers? Is that countable? Where would we start? What's the successor function?
0.
So if it's positive, 0 is not technically defined to be positive.
2.
2, yeah. So we can start with 2. What's the successor function?
4.
Add 2 to the next is the previous plus 2. Loop that process forever, and you would eventually hit any particular even integer query. You won't hit all even numbers if you define a certain amount of time or a certain number of iterations this process runs. We don't exhaust this infinite set, but you can't give me an even integer, an even positive integer that we wouldn't eventually reach. So it is countable. Let's go back to that first example, the set of all integers. Now this is positive and negative. Is this countable? Okay, we have to vote. Who says no, the set of all integers is not countable? Who says yes, the set of all integers is countable? More people say it is countable than it's not countable. Interesting. So if it is countable, where do we start? What's the successor function? Negative infinity is not a number, unfortunately. It's an idea. It's the idea that the negative integers would go on forever, but it doesn't give us an integer to start at because negative infinity is not an integer. Start at zero. Start at zero? I like it. Why zero?
Because from zero you could add or subtract.
Add or subtract. So how do we define a successor function from a number in that case? You could add or subtract, but then you'd be doing one or the other. If I added one, how would I get to negative? You can define a non-deterministic process, but we can't have that in the idea of something that is countable. Although you could expand that non-deterministic process. Since there are only two threads, you could start to alternate between what is defined as the successor in those two threads, and then try to collapse those into a single function, since that would be possible. Let's see if we could do that. Let's define a sequence of integers that starts at 0, then goes to 1. The sign is going to flip and go to -1, then 2, then -2, then 3, then -3, on forever. Do we agree that this sequence would eventually hit any particular query integer? So how can we mathematically define this? We're going to define that this is the 0 index, the 1 index, the 2 index, the 3 index, the 4 index, the 5 index, the 6 index, etc. Or you can define this as the 1 index. It doesn't really matter whether it's 0 indexed or 1 indexed, but spend a couple minutes, come up with a function. This is your index, and this is your number. We want some f of I to give us n. What is that function? Actually, going to be slightly easier if we one index this. Let's do that for a moment. Anything you can do one indexed, you can do 0 indexed, but I think the function is ever so slightly simpler. We one index instead. what are kind of the two components of that function. We can mathematically figure out how to do those two components and throw those together. So maybe it's worth splitting those apart, figuring out how do we do each of those components, then how do we put them together into a single function. Feel free to put heads together if you're starting to think about things and or are stuck.
I don't know if I wrote it down.
Yes.
Plug in some values. See if you get out what you expect.
I don't know about.
She left me in the dust.
What
I
happened?
went like this, put our heads together, and she left me in the dust.
Oh, it's unfortunate.
You want me to say that out loud? Or
Sure. What do you have?
like n plus one minus two and that works. I just don't know if that's the.
You want to use I as your variable. Yeah.
Okay.
So I plus 2 minus 2n, is that what you said?
I plus.
I plus 1 minus 2n.
Yeah.
Let's see if this works. All right, for 0, we're going to add 1. So 0 plus 1 is 1, minus 2 times 0. So when I is 1, n is 1. How am I reading that? So maybe this is 0 indexed. We say 1 plus 1 is 2, minus 2 times 1 is 0.
I might have messed that up. Let me read.
Yeah. Not what I'm anticipating the answer to be, but it's a good guess.
Yeah.
Anyone else with some ideas? Either for 1 or for 2? But mathematical idea gives us either one of these components.
I see. Oh my god. So. Oh.
I think what I'm learning is I need to go yell at our math professors.
Use a piecewise function.
It's not quite piecewise, but that's a good idea. I think we can basically multiply these two things together, and we end up with what we want. Since alternating signs is going to give you something positive, something negative. Here we have our sign, here we have our magnitude. How do we just alternate signs? We don't care about the magnitude, we just need the first number can actually be negative because negative 0 is the same thing as 0. So negative, positive, negative, positive, negative, positive, negative. If we're multiplying, then we want that to be -1, +1, -1, +1, -1, +1. So we don't care about the magnitude. How do we get that sequence out of a function? Yeah. So first part of this, we're going to say n equals -1 to the I. When you plug in 1, -1 to the -1, sorry, -1 to the 1 is negative. -1 squared is 1. -1 cubed is -1. -1 to the 4th is 1. These alternates. Excellent. So we have part 1 is done. Now we need to multiply it by the magnitude. How do we increment something every 2? How would we do this in a program? I want you to print 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. How do you define the loop parameters to do that? I think the easy way to see this is that some of these numbers is really easy. Let's look at 2. How do you go from 2 to 1?
Divide by 2.
Divide by 2. How do you go from 4 to 2?
Divide by 2.
Divide by 2. How do you go from 6 to 3?
Divide by 2.
Dividing by 2. So it seems like dividing by 2 is going to be a pretty good idea. How do we get from 3 to 1?
-1 divided by 2.
-1 divided by 2, or the floor of divided by 2? There we have it. So we have a way of converting from, notice what the indices are. The indices are the positive integers. Didn't we say that the positive integers are countable? So we now have a function where we can take the countable positive integers, throw them into this, and produce a sequence that is going to produce all of the integers. A really interesting result comes from this. So the question that I will ask from you is, which of these sets, the positive integers or the integers, is larger? Which one has more elements?
Neither.
Because of this equivalence, they are the same size. That's interesting to think about, because one is a subset of the other. How can you have two sets where one is a subset of the other? Like, all of the positive integers are contained within the integers, and there are some integers that aren't positive integers, but they're the same size. And that is the fun of infinity. Because they go out forever, what determines the size of a set is, can you map one set onto the other set? And are there elements left over that are unmappable? And we were able to map the positive integers onto the integers in a way that you give me an integer, I will always be able to give you the positive integer for which that integer is the index in this set, in this function. Because we have a mapping that has no hole in it, it has no asymptote, it's a straight linear function. Okay, it kind of alternates between that, but there's no there's no discrete value of this that this would not reach. And that's really interesting to see and to conclude. These sets are the same size. Very counterintuitive result that a lot of people will try to fight me on, and they will be wrong. But this is the reasoning if anyone ever asks you. So, cool. The set of all integers is countable, and this is the outline of the start of a proof. This is the intuition behind a proof. All right, next question I have. Are the set of rational numbers countable? First, we should define what is a rational number?
Action.
Something with a fraction. We have a numerator over a denominator. So any number that can be represented with such an n and a d, representing a numerator and a denominator. So this includes things like 1/1042nd, 3/763rds, -9/19, but also duplicates like 2/4, 3/6, 4/8. So are they countable? Anyone want to intuitively assert, yes, the rational numbers are countable? One person, two people. Anyone want to assert, no, the rational numbers are not countable? Seems like a lot of people have no idea and we're guessing. That's fine. This is not a straightforward concept. Turns out the rational numbers are countable. The real question is how? How are the rational numbers countable? Any ideas for how we would enumerate the rational numbers, come up with a function that would, given any query, eventually generate that rational number? Okay, I'll show you. It's fun. I'm going to throw a copy of the set of all integers on each axis. 0, 1, -1, 2, -2, 3, -3, etc. forever. 0, 1, -1, 2, -2, 3, -3, on forever. Do we agree that we could basically have the row represent the numerator, the column represent the denominator? Is every rational number somewhere in this infinite table? The issue is, we start iterating the first row, we never get to the second row. We start iterating the first column, we never get to the second column. So how do we define a successor function? Any thoughts? How could we enumerate this entire table? Diagonally. This is going to be the first number we look at, the second number we look at, the third number, the fourth, the fifth, the sixth, the seventh, the eighth, ninth, 10th, etc. We're going to create an index out of diagonally looking at this table. I'm not going to have us come up with that function, at least not yet. That would be a fun thing to do eventually, to come up with how do we convert between an input row column pair and the order in which we're going to look at it. But it's very possible to do. And in fact, we will have then mapped every possible rational number to some positive integer that we've already proven is countable. And since the indices for this are all integers, we know that those are countable by the prior proof. So we can now state the rational numbers are countable. Again, this is not a rigorous mathematical proof. This is just the intuitive idea. But as a computer scientist, very frequently, all you are doing is implementing something. So what you should know is whether it is possible to do something or not necessarily how to prove that it's possible to do it. You should be able to know how to do it. Any questions on either of these ideas? Do note that some of these fractions end up being the same absolute value, or just the same value in general, like 0 over 1, 0 over -1, 0 over 2, those all are 0. And 1 over 2, 2 over 4, 3 over 6. There are an infinite number in this table of every possible rational number. And that is strange to think about. Any value you give me, you just multiply the row and the column, and you end up with an unlimited number of copies of that as this table goes on forever. So every single rational number shows up in this table an infinite number of times. Interesting. Anyone need anything before I erase? These ideas are going to come back to us when we talk about Turing machines. So it's worth thinking about them as an aside for how we do these, because understanding this at an intuitive level will help us to understand things like whether machines terminate or not, whether programs terminate or not when run on a machine. There's nothing like theoretical computer science to show us that this is really just the study of theoretical math, which is fun. All right, we've seen a bunch of sets that are countable. What's a set that's not countable? Where no matter what we decide for how we are going to enumerate this set, there will always be some value that someone could give you that your iteration algorithm would not reach.
Set of all real numbers.
Real numbers,
Prime integers.
prime integers. They don't necessarily have a successor function. And in fact, we haven't, I don't think, proven that the primes are infinite. I think we have. Primes are infinite, but twin primes we don't know. But yeah, there's not necessarily a successor function, so we need something much more complicated than that to be able to prove whether they're countable or not. We could have a way to generate the next prime from the current prime. But there is kind of a way to do that. It's not a direct function, but there is an algorithm that we could write. Try every number that is larger than this number until we hit the next prime. That is not a proof that it is countable, because just because this program has been running for 10,000 years and generated the next prime and the next prime and the next prime, that doesn't mean that there are an infinite number of primes. It could be that the last prime that we saw is in fact the last prime we would ever see. And just because our program has been working and gone over 10,000 numbers without finding a prime doesn't mean we can conclude and say there are no more primes, because maybe the next number is a prime. We don't know. So that's an intriguing idea. But I'm going to attach ourselves to the other idea here, the set of real numbers. And in fact, we can constrict the set of real numbers to a very small slice of real numbers. Let's just look at the set of real numbers between 0 and 1. Is that countable? Remember that real numbers are, they include all the rational numbers, but they're also all decimals that infinitely repeat, that go on forever but don't repeat. So for instance, pi is a real number, but at least as far as we know, goes on forever. E, another such number. There are more of those between 0 and 1 that we haven't assigned a value to, but they exist. What do we think? Real numbers, countable, uncountable? How would you come up with an enumeration procedure for the reals? One idea would be something like, okay, I'm going to place the decimal and I'm going to enumerate all decimals of length 1. So 0, 0, 0.1, 0.2, 0.3, all the way to 0.9. I'm going to restart 0.00 all the way up to 0.99. I'm going to restart 0.000 all the way up to 0.999. Continue this process forever. Does that work? Would this process ever generate 1/9? The answer is no. There are an infinite number of ones after the decimal in 1/9. This is all numbers of length 1, length 2, length 3. We never get to infinity. We keep getting larger and larger and larger. There's no integer we wouldn't get to, but this is why infinity is not an integer. We're not going to get there. We're not going to ever generate 1/9 or any other infinitely repeating decimal, or any decimal that does not repeat but also goes on forever, like a pi, like an e. None of those will be generated by this procedure. So how in the world could we generate a procedure that counts these? This to me is the most intuitive idea for getting started, but in fact, it's not possible. And we can prove that it's not possible. How would we go through a proof of proving that it's not possible to enumerate all of the real numbers between 0 and 1? This is what smart dead mathematicians are for. They've done this already, and we can just take their idea and say, wow, that was brilliant. So this is Cantor's diagonalization theorem. I guess it's technically a proof, so it's Cantor's diagonalization proof. But the idea is that it's a proof by contradiction. We are going to assume that it is possible to enumerate all real numbers between 0 and 1. And in fact, we're going to place them in a list on forever. And then we're going to have the place in here on this axis. So this is the first indexed place, the second indexed place, the third indexed place, the fourth indexed place, etc. So this is the place. This is the number. So they're all going to start with 0 point something, with the exception of 1, which would be included, but that's somewhere in here. So just imagine that there's a hidden 0 point before this 1. But in this case, it doesn't really matter the order that we write them down in. We just know that it is possible to write them all. So however it is that we do this, I'm just going to come up with some numbers. Doesn't matter what the rest of these are, but these numbers go on forever. Each one of them goes on forever, or not. They might stop at some point, but doesn't matter. We need to figure out whether there is a number that is not in this table. How could we determine this table goes on forever, but we want to, the purpose of this is to come up with some number that is not in this table. And the way we're going to do it is we're going to modify each number in each place so that we get that free 0 point here, And whatever is in the first number in the first place, we're going to take a look at the diagonals here. And we're going to modify the diagonal in some way to make our new number. So we're going to take this 1 and we're going to add 1 to it. And now this number is different from this number in this place. We're going to take this digit, we're going to add 1 to it. And now this number is different from this number in this place. We're going to take this number, we're going to add 1 to it. And now this number is different from this number in that place. You continue this process forever. If this number had stopped, it's just 0.5. It's the equivalent of 0.50000000. So if there's no number there, just replace everything else with zeros. And that way you can make this a 1 where there was that 0 and it's different from that number in that place. So this process goes on forever. This process goes on forever. But the end result is we are making a number that is not in this table anywhere. And that is the contradiction. If this is truly infinite and truly complete, then it should not be possible to generate a number that's not in the table. But now we have a process that will iterate through and create an infinitely long number via the infinite number of numbers in the table that is different from every number in the table in at least one place. So in fact, the set of real numbers, even constrained to an arbitrarily small window, all real numbers between 0.000001 and 0.000002 is infinite and not countable. Wild. Any questions on that idea? Again, this will all come back to us when we start talking about an important nature of programs and an important limitation of the modern computer. Because the modern computer really is just doing this. So, set of real numbers is not countable. Why do we care to distinguish between them? As I've shown, for any set of countable, for any countable set, we can prove that they're countable producing an enumeration procedure, giving us, very much like induction, a starting point and a process to generate the next one, and or just a function that converts and index the set of all positive integers that we know is countable and map that onto the query set. If we can do that, then what we have is a countable set. So do note that that process does not terminate because we are doing a conversion between every single one of those numbers. But the important thing is it produces something that is well-defined, that is predictable, and in terms of what I can disseminate to you, you can't give me a number for which it doesn't work. What's nice about this is it means it can also be simulated on a Turing machine via a program. And maybe a program that runs forever, but simulated on a Turing machine. And as a process, we could run a program to do that. We could also simulate it on a Turing machine. Here's an example. The input alphabet is ABC, and the set is the positive closure of that alphabet. Is the set countable? What do we think? Countable? Not countable? Yeah.
Say countable.
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 How do we enumerate it? So there are multiple different possible enumeration procedures for this. Some of them will never terminate, but some of them will. So as long as there exists some enumeration procedure, then the set is countable. As an example, we could look at all integers and just say start at 0 and add 1 as our successor function, and that never gets to the negative integers. We can't conclude that it's not countable from that. We just haven't found the appropriate enumeration procedure that proves that it is countable. So how could we address this set in a way that shows that it's countable? Idea number 1. We're going to list the strings in alphabetical order. Does this create an enumeration procedure? Any thoughts on that? We list these in alphabetical order. What's the first string?
A.
A? All right, I'm just going to start writing a set. A, what's the next string? It is not AB. AA is the next string. What's the next string? AAA? This process will go forever. Are we ever going to write a string that has a B in it? No. So this is not an enumeration procedure because it does not, you can give a counterexample. You say, the string B, at which index does your enumeration procedure output B? And with this enumeration procedure, there is no index that is B. This process goes on forever and continues producing strings in this language. But it's not an enumeration procedure because there are strings in a language that it never gets to, no matter how long it runs. You can get up to 10,000 A's, 10 trillion A's, doesn't matter. We'll never reach B or AB or CCBA. None of those strings will be reached by this procedure. So what can we do instead? Is there another algorithm, a way of ordering the strings in this language such that we could prove that it is countable? So this was not. Anyone with an idea? How could we do it? There is a way. This is countable.
Just spitballing, is it logically similar
Yeah.
to the enumeration procedure for rational numbers?
Interesting. Using a kind of a two-dimensional table,
Well, I was thinking it would be three-dimensional because there's
3 characters, and find some way to, yeah, you probably could find a way to do that. There's a simpler way to think about it, but that would reasonably work. It's kind of non-deterministic in nature, but you could search that non-deterministic space in a way that is very much like the diagonalization of a two-dimensional table. The easier way to think about it, since we're basically running out of time, is that we list them in length order. We list all strings of length 0, of which there are none, all strings of length 1, of which there are 3. We would list A, then B, then C, then all strings of length 2, AA, AB, AC, BA, BB, BC, CA, CB, and CC, and continue this process for all strings of length 3, strings of length 4, strings of length 5. There are a finite number of strings for every possible length order, even though it grows exponentially. But if we did this, could anyone assert a string that this process would not eventually reach? That is, of course, in this language. And the answer is no. This would eventually get to any string, any query string. So, in fact, there is a way to do it. So the result from this is actually really interesting. The reason we asked this question is that it turns out that Turing machines are countable. How do we show this? Well, if Turing machines can be represented in binary, we have some way of taking that quintuple and turning that down into each one of those elements, so zeros and ones, followed by some separator character of some kind that tells you where each of those begins and ends. Then what about the binary numbers? Are the binary numbers countable? Yes, because we can map them onto base 10 numbers. So it turns out some of those are going to be legal Turing machines, but some of them are not. We could generate a procedure that just increments binary numbers, asks, is this a Turing machine? If yes, add it to the list of possible Turing machines. If no, toss it out, increment, try again. We can, in fact, create a procedure that generates every possible Turing machine. That's the equivalent of saying, I could write a program that is going to output potential programs in that language. I'd write a Java program with the task of outputting Java programs. I would go through every possible character, every possible length, and eventually I would output something that is syntactically legal in Java. And that process would continue to vomit out programs of different lengths. If you wrote some program somewhere, my program would eventually generate your program. It might be a very, very, very long time from now, but it is possible to write a program that generates every possible program. What a weird thought. I'll leave you with that, and we're going to come back and talk about this more in a little bit more detail tomorrow. Hope I didn't break too many brains. Office hours starting now. If you have any project questions or homework questions or anything else,